Hi everybody, it's Professor Mitchell. We're continuing Chapter 3 on numeration systems and whole number operations. And today we're going to be looking at Section 3.3 on subtraction of whole numbers. We'll look at the meaning of subtraction by studying various models, the inverse relationship between addition and subtraction algorithms, including the standard algorithm and how to use them, subtraction with number bases other than 10, and finally, mental subtraction computational skills and estimation techniques. Subtraction of whole numbers can be modeled in several different ways. First, we have the takeaway model, which views subtraction as a second set of objects being taken away from the original set. We also have the number line model, where subtraction is represented by moving left on the number line a given number of units. And we have the missing addend model. An algebraic type of reasoning is used where students compute a difference by determining the value of an unknown addend. So here's an example of the takeaway model. You start with 8 blocks, take away 3 blocks. You have 5 blocks left. So this is a model of 8 minus 3 equals 5. And then in the number line or measurement model, this is a way, in this example, of modeling 5 minus 3. You start at 0, move 5 units to the right, and then move 3 units to the left. And wherever you end up would be the answer to 5 minus 3, the difference of 5 and 3. In the missing addend model, 8 minus 3 equals what? This can be thought of as the number of blocks that must be added to 3 in order to get 8. The number 8 minus 3 is the missing addend in this equation. 3 plus what equals 8? The answer is 5. So you've all taken algebra, so in your algebra class, this probably would have been written as 3 plus x equals 8. Of course, when you're dealing with elementary school students, you wouldn't necessarily write it like that. In the missing addend model, this can also be modeled by sets. So if the total number of objects in this set is 8, and I have 3 of them over here, how many must there be over here? Here's that same problem modeled with the number line model. All right, so this is modeling 3 plus what number equals 8. The definition of subtraction of whole numbers is for any whole numbers a and b, such that a is greater than or equal to b, a minus b is the unique whole number c, such that b plus c equals a. We're going to say more about this in a little bit, but notice this requirement that a is greater than or equal to b. The first number has to be at least as big as the second number in order for the answer to be a whole number. Next, we have the comparison model. If Juan has 8 blocks and Susan has 3 blocks, how many more blocks does Juan have than Susan? And you can see a model of that here. Notice the one-to-one correspondence between Susan's blocks and Juan's first 3 blocks. It can be shown that if a is less than b, then a minus b is not meaningful in this set of whole numbers. And of course, you know that if a is less than b, then a minus b is going to be a negative number. And that's probably not going to come up in an elementary school situation. Negative numbers are traditionally not introduced until pre-algebra. And I mentioned this to you in the last video. What that means is that subtraction is not closed on the set of whole numbers. In other words, the difference of 2 whole numbers is not necessarily a whole number. If a and b are whole numbers, then a minus b is not necessarily a whole number. Introductory algebra using whole number addition and subtraction. Sentences such as 9 plus 5 equals sunshine symbol and 12 minus diamond equals 4 can be true or false depending on the values of those 2 symbols. For example, if the sunshine symbol is equal to 10, then 9 plus 5 equals that symbol is false, because 9 plus 5 equals 10 is false. If the diamond symbol is equal to 8, then 12 minus the diamond equals 4 is true, because 12 minus 8 does equal 4. If the value that is used makes the equation true, it is called a solution to the equation. Now we get into some subtraction algorithms. So here's a concrete model for 243 minus 61. So we're going to represent 243 with 2 flats, 4 longs, and 3 units. To subtract 61 from 243, we try to remove 6 longs and 1 unit from the block shown in the figure. We can remove 1 unit, but to remove 6 longs, we have to trade 1 flat for 10 longs. So you can see that's what's been done here. We've taken away the flat and traded it in for 10 longs. Now we can remove or take away 6 longs and 1 unit, as seen here, leaving 1 flat, 8 longs, and 2 units, which represents 182. Next, we have the equal additions algorithm. The equal additions algorithm for subtraction is based on the fact that the difference between 2 numbers does not change if we add the same amount to both numbers. Now be careful not to get this confused. We did something similar with addition, but when you're adding the 2 numbers, you have to add to one number and take away from the other number. All right. When you're doing subtraction, though, you add to both numbers. So for example, we can make the problem 255 minus 163 easier by adding 7 to both numbers. That will turn this last digit into a 0. And then we can make it even easier by adding 30 to both numbers. That makes the second number 200, and it's very easy to see that 292 minus 200 is 92. So that would also be the answer to our original problem. The counting up algorithm can best be described as the making change method. It is the way that cashiers and tellers used to give change for purchases, but today with calculators and computerized cash registers, it's become sort of a lost art. So you see this less and less frequently. It tends to be older cashiers who still do this, you know, because maybe when they first started, they didn't have the same kind of cash registers that we have now. It is a way to do subtraction in your head. It uses the idea of the missing add-in method or model for subtraction. Students are encouraged to count up to nice numbers, which are multiples of 10, 100, 1000, etc. So for example, subtract 100 minus 31 using the counting up algorithm for subtraction. So we're going to start with the number 31. In order to get to the next higher nice number, which would be 40, you have to add 9. And then to get from 40 to the next nice number, which happens to be the first number in our subtraction problem, you have to add 60. So since we added 9 to get to 40 and then added 60 more to get to 100, that means that the difference between 100 and 31 is 69. Here's an example of the counting up method used for making change. Noah owed $11 for his groceries. He used a $50 bill to pay. While handing Noah the change, the cashier said 11, 12, 13, 14, 15, 20, 30, 50. How much change did Noah receive? So when the cashier first said 11, he or she had not handed Noah any money yet. But when they said 12, they handed him a dollar bill. When they said 13, they handed him another dollar bill, another dollar bill, another dollar bill. When they went from 15 to 20, they handed him a 5. When they went up to 30, they handed him a 10. And when they went up to 50, they handed him a 20. So if you add all of these amounts together, you get $39. Thus, $50 minus $11 equals $39 because $39 plus $11 is $50. The trade's first algorithm is very similar to the standard algorithm, except that all regrouping is done before any of the subtraction is carried out. Using base 10 blocks may help with students understanding how to subtract. Next, we come to understanding subtraction in bases other than 10. So the problem here is 4, 3, 2 in base 5. We're going to subtract 4, 3 in base 5. Notice the addition table over here. An addition table is still helpful for doing subtraction. Although in this case, we don't have to use it all that much because they're not using the standard algorithm. They are actually using an equal additions algorithm. So what they've decided to do, they looked at this 4, 3 in base 5. Remember, you can think of this as 4 nickels and 3 pennies. If I add 2 more pennies to 4 nickels and 3 pennies, I end up with 4 nickels and 5 pennies. I can then trade the 5 pennies for a nickel. So now I have 5 nickels. Now I can trade the 5 nickels for a quarter. And that's why 4, 3 in base 5 plus 2 comes out to 100. So again, think of it as if you have 4 nickels and 3 pennies and you add 2 more pennies, you really have a quarter. All right, and then it's very easy to add 2 to 432. It just gives you 434. And then it's very easy to subtract 434 minus 100 is 334. So again, that's using the equal additions algorithm. You can also use the standard algorithm in bases other than 10. Here is a blocks model for, again, we're in base 5. So the problem is 3, 2 minus 1, 4. So here are my 3 longs and 2 units. Again, you can think of these as 3 nickels and 2 pennies. In order to take away 4 pennies, I have to trade in one of these longs for 5 units. And let's see, what did they do here? Oh, yes. So notice there's 2 units here, but after I traded in one of my longs, I have 5 more units. And now I can take away 1 long and 4 units. I'm left with 1 long and 3 units, which means that 3, 2 minus 1, 4 is equal to 1, 3. I just want to point out, and I'm sorry about this, that they're trying to show you the standard algorithm, but their numbers don't really line up all that well. So ignore this, all right? The 2 should be here. Let me try to talk you through this. So I can't take 4 from 2. That means I have to take one of these, which leaves 2, and trade it in for 5 of these, all right? And so using the addition table on the previous slide, let me just jump back to that for a second. We want to know what is 1, 2 minus 4. So think of that as 4 plus blank equals 1, 2. So here's 4, here's 1, 2. The missing addend is 3. Okay, so that's how I get the 3 here, and then 2 minus 1 is 1. All right. Mental computation. First, we have breaking up and bridging. So if I'm trying to do 74 minus 26, I'll start by taking 20 away from 74 because that's a nicer number. 74 minus 20 is 54. And now I have to take away 6 more. 54 minus 6 is 48. Trading off. That's really the same thing as the equal additions method. So it would be easier to subtract 30 than 26. So if we add 4 to both of those numbers, we come up with 78 minus 30. It's very easy to see that 78 minus 30 is 48. And then dropping the zeros, this is when you're subtracting numbers that end with zeros. We do this without even thinking about it. So for example, 7,400 minus 600, just think about 74 minus 6 is 68. That must mean that 7,400 minus 600 is 6,800. And that's going to take care of section 3.2. Thanks for watching.